Alright, so hello everyone, my name is Viraj and today we are going to have post-contest discussion for Leetcode 412. Alright, so we'll be discussing all 4 problems. Let us start with problem number 1. Alright, so final array state after k multiplication operations 1. So I mean the question name is pretty simple to understand, and that is how actually the question goes. And this is part 1, so there is obviously going to be a part 2 to this. And I think today's contests were all about this thing only. They had like one part of each question and then the second part of that question same, making a total of 4 questions. So let's solve part 1 and then we'll be looking at part 2 in the upcoming minutes. Alright, so we have part 1. You are given an integer array nums, an array k, an integer k and an integer multiplier. Now you need to perform k operations on nums. In each operation, find the minimum value x in nums. If there are multiple occurrences of the minimum value, select the one that appears first and then replace this selected minimum value x with x into multiplier. And then when you are able to perform these k operations, simply return the final state of nums. So it's a very simulation based problem. Alright, if you look at the current array right now, let's say the array is 2, 1, 3, 5, 6 and k is 5 and multiplier is 2, then they have actually shown you the 5 operations. Yes, you actually start off initially, you look at the array and you like, alright, what's the minimum in this array? The minimum is 1. So you say, alright, identified 1, multiplied with 2, and then that's my one operation. So after one operation, my array looks like 2, 2, 3, 5, 6 because this 1 has been multiplied by 2. Now next time you again identify the next minimum in this array. In this array, the next minimum is 2. But which 2? This 2 or this 2? They have already cleared that part. If you have multiple occurrences of the minimum value, select the one that comes first. That means if I have 2, 2, then I will select this 2. That's the 2 that comes to the most left hand side. Now I select this 2, multiplied with the multiplier, that's 2, and it becomes 4. So after operation 4, my array looks like 4, 2, 3, 5, 6, and then 4, 4, 3, 5, 6, 4, 4, 6, 5, 6, and then 8, 4, 6, 5, 6, and that is the final answer after the 5 operations. Alright, so a very simulation based problem. It's not about at all thinking like what should I actually do in this question logic wise. If you think simply and see the tag on this problem, it's like the first problem of the contest today. It's an easy problem. That means it can be solved by simple brute force and simulation. That's one observation, and the other part is obviously I can look at the constraints. I know k is only 10. That means the max they are trying to ask you is 10 operations. You now don't perform this simulation more than 10 times. And what is the maximum size of the array? That's 100. So what is the largest size of the array on which you will perform this simulation is 100. So let's try to whip up a pseudocode, alright, to understand the time complexity, just for the beginners out there. And then we'll see if I code this up, how will it look like and will it actually work, alright. So now I said that k is very small, like k is an order of 10, correct? And then I said n is an order of 100. So let's take the very maximum case. I'll say I have the largest array possible, that's of 100 elements. And then I have k equals to 10, that's the highest number of operations I want to perform. Ideally, if I want to simulate this process, I could have written, let's say, a while loop, right? To exhaust k, right? K minus minus, exhausting k till I think k is still greater than 0, I want to exhaust k. And then what is the simulation? You want to identify the minimum in this current array. So let's say whatever is the array, let's say this is called array. And let's say this array is of 100 size, then you want to identify what is the minimum in this array. So how do you do that? In a very brute manner, I can very simply say, let me run a for loop. Let me run a for loop in this array, identify what is the lowest element, let's say lowest element LE. And then for that lowest element, what's the index at which that lowest element is kept, right? If I have multiple lowest elements, then I'll be like, I want the first index. I can just do that thing obviously in the for loop itself. And when I come out of this part, all I need to do is at this particular index location, I want to simply multiply the multiplier value that's given, to me. If I do this, I will very well simulate this process and I'll get the new value in place of that value which is getting multiplied by this multiplier value. And now if you look at the time complexity, obviously I have a while loop which is exhausting in k operations. So I can say this is O of k. And then I have an inner for loop. Let's look at this. A for loop is obviously going to run from I equals to 0 to I less than n because it's basically iterating on the whole array. Simply means order of n. So what is the net order of this complexity? This is O of n into k. Now order of n into k, does that seem feasible? Obviously. Why? Because if n is 100 and k is 10, then you will maximum form a O of 1000 solution. And O of 1000 solution is definitely less than the TLE limit, that's like 10 power 6 or 10 power 7, whatever you take at the upper bound, and that means definitely going to work, definitely going to fetch you an AC, not at all going to give you a wrong solution. Alright, so all we need to do is simulate the process as expected, and that's very ideal in this case also because we have a good experience of how Leetcode works. Leetcode problem A is mostly about simulation or some very simple mathematics, and for all the beginners out there, you can note this, that most problems in Leetcode contests, at least for the first or second problems, requires basic simulation. So that's what I'm doing. I know if I run a basic simulated problem, I am running into a time complexity that is well achievable. So why not code it up quickly and get an accepted solution? Alright, so let us look at the code part now. Just how I explained in the pseudocode, that's what I have just copy pasted. I'll say, alright, start off with the size n, that's of the array. Then run a while loop k minus minus. Then I have a minimum number. Since I want to minimize this, I'll start with int max, and then I have the index, that's the place where that minimum number is. I start off with -1. Then I'll iterate in the whole array from 0 to less than n. If I think that the current minimum number is greater than nums of I, not greater than equal to, remember, why greater? Because I know if it's greater than equal to, then also I don't want to update my index since I want the leftmost part, right? How does that make sense? Let me just quickly explain this part for the beginners. Let's say you have 2, 3, 4. In this, the minimum is obviously 2. That's very obvious. But do you want this 2 or do you want this 2? Obviously, you want this 2. Yes. So if you want the first 2 that's kept at the 0th index, what can you do? Once you try to minimize your number, let's say your number was very large right now, and you minimized it and said, yeah, 2 is the new minimum. So when 2 is the new minimum and the new updated index is 0, then do you later want to update your index with 1? No. Although this 2 is minimum, but it's equal to that minimum. If I would have gotten some value that's even lower than this, then maybe I could have updated the index. But if it's not less than the current minimum, it's equal to the current minimum, then I also don't want to update my index. Because remember, I am not trying to find the minimum value, but I'm rather trying to find the index where that minimum value comes. And in case of collision, I want that that I receive the index which points to the leftmost minimum value. So if I again receive that minimum value back, do I want to run inside this if logic and update my index to I, the index where the minimum is getting stored? No. That's why this is not greater than equal to, this is greater than. Alright, now when I say nums greater than, so this becomes minimum number greater than nums of I, then I'll update minimum number equals to nums of I, index becomes equals to I. And when I come out of this for loop, obviously the index is where I have the lowest number stored currently in the array, and then I can just multiply that number with the multiplier, and then this simulation goes on till k times, and I simply return nums after this. Now what is the time complexity? As I explained, this runs in k order, and this runs in n order. So what would be the time complexity? We would have O of n into k. What about let me write it like this, Tc equals to O of n into k. What about space complexity? Obviously, I'll have space complexity as O of constant. Why constant? Am I using any extra space? No. I have the same array. I am actually modifying that same array, and I'm just using some constant variables to calculate my index and minimum number. Do they take any extra space? No. Technically, I can call that as constant. So space becomes constant, space complexity becomes constant, time complexity becomes n into k, which in roughly highest order becomes O of 1000. Definitely works, gives me a right solution. So if I submit this out for you, all right. So we can see, yes, it's going to give me an accepted solution. All right, great. Let us move on to the next problem. All right, so problem number 2, that is count almost equal pairs 1. So again, first part for something, obviously there's going to be the second part. We'll understand that in the upcoming minutes. All right, so this problem, again, second problem, very simulation based problem. If you look at a very first go, it's a medium rated, and if you're looking out for for the beginners, you can just think of simulating this problem, and that would be decent enough. All right, so what we'll do is we'll read the problem. You're given an array nums consisting of positive integers. All right, great. Now we'll call two integers x and y in this problem almost equal if both integers can become equal after performing the following operation at most once. What is the meaning of at most once? Means either you don't perform it or you say I'll perform it only one time. I don't perform it above one times. All right. Now what is that operation? That operation is from this x or y, you either choose x or you choose y. Let's say I choose some number out of x and y. Let's say I choose x. I can then swap any two digits within that chosen number. So I'll pick up any two digits and I'll swap them in that chosen number. And then when I do that, I'll check whether they became equal or not. So I'll ask, return the number of indices I and j in nums where I is less than j, such that nums and I and nums of j are almost equal. So that is the ideal case. If choosing x and y, or let's say choosing some nums I and nums j, if I swap any one, I choose any one number and swap any two digits inside that chosen number, those numbers should now become equal. If they become equal, then I can very well say, yeah, it's good to go. I am great, and like the pairs are great basically, and I can count that as almost equals pairs. And then the total answer is what they are asking for you. The total count of almost equal pairs is what they are asking to you. All right, so now they have given you one small line which is very, very important. Note that it is allowed for an integer to have leading zeros before performing an operation. Now what does this mean? What does this mean? What can happen is, I'll give you a brief explanation over here only. Let's say there's a number that looks like, let's say single digit, 5. Let's say it looks like 5. Now what can happen is, if you're trying to compare this number to 50, so you will be like, oh, can I compare 5 with 50? If this is, let's say, nums of I, and this is, let's say, nums of I, and then let's say this is nums of j, then can I say that they are almost equal? Now at a first glance it might seem no, they doesn't seem to be equal. And can I swap anything? I only have one digit in this. Can I swap anything in nums of I to make it? No, doesn't make sense. Maybe I can swap anything in j, right? That's one true. But the other logic is, look at it like this. Actually, this number 5 can be written something like 0, 5, right? Definitely the 0 that comes before 5, or simply I'll copy paste this over here, 0, 5. This 0 over here is the 0 that comes before 5. Although currently it doesn't hold any significance since it comes before the 5 value. But what if now I say that just imagining the 0 was there, I would have swapped these two values. If I swap these two values, or these two digits, rather, then can you say nums of I became 50? Yes, it became 50. And that means now nums of I and nums of j have become equal. So this is the trick part in this, right? You cannot say that just because you had some place of ending, that means you cannot consider the zeros that comes before it. They can also, or they should also be considered. So we'll also tackle that case. We'll understand how. But let's now come to the examples and we'll understand much better. So let's say over here only. All right, so they have given this example, just how I quoted. Let's say the array is 3, 12, 30, 17, and 21. So the argument is, according to them, there are only two pairs. What are the two pairs? One pair is 3 and 30. Why? Either if you pick up this y and this as, let's say, if this is x and this is y, then maybe in this y you swap 3 and 0. If you swap 3 and 0, it becomes 3. Now 3 is equal to 3 and you get the correct almost pair, that's 30. But the other thing can also work, right? If let's say this was 3 and this is 30 and I want to choose this, how can I do? I can say the 0 that is not currently looking over here, because obviously why would I would write that 0 in the integer format, but technically that 0 is still there. So if I replace the 0 that comes before this 3 with this 3 now, and I swap that, this number becomes 30. That's x, and now 30 is equal to 30, and again almost equal pair. So gets counted. Either way, you know that 3 and 30 is almost equal pair. So I'll count that 3 and 30, and then 12 and 21. Very obvious. If you replace, let's say 1 and 2, swap them, it becomes 21. 21 is equal to 21, good to go. Or if you go for 21, you can just replace 1 and 2. Same thing, same case, it becomes 12, and in that case also almost equal pair. So their claim is you cannot make more than 2, and to check that, we don't need to actually cross-reference that part, just because we can say, yeah, okay, for the example, the output must seem true. Otherwise, if you still want, for the beginner, you can actually draw this on your pen and paper, pick up all the possible combinations, and you will very well realize that, yeah, this is the only two cases where I think I have almost equal pair. Now, for example 2, similarly, they have some answer. Example 3, they have some answer. All right. Now, the main thing is, this is the second problem for Leetcode. All right. And when we are trying to simulate a process in our head, the first thing that comes into picture is, what are the constraints? Let us look at that part. So nums is very small. Nums.length is very small. It's in 100 order. That means total size of the array is 100. And then a very interesting point is, nums of I is in 10 power 6 order. That means if I ask you, what are the maximum number of digits nums of I can have? Let's frame this again. Maximum number of digits nums can form. That is basically simply saying 6. Why? Because I have 10 power 6 as the highest value of nums of I. So if 10 power 6 gets represented like this, like 10 power 6, that means 1, 2, 3, 4, 5, 6, 7, something like this. So, alright, not 6 actually, 7 rather, right? If you have the highest number, if you have the highest number like this, then it is 7. So, in general, you can say that I have a total of 7 maximum digits that a number can have. Above that, I know I cannot go. Can I have any more digits than this? No. Now, why is this important? Let's try to understand this. If I ask you this question in a very brute manner, what is going to be your first idea? Your first idea can be very simple. I want to swap any 2 digits in a number. So, after, let's say I have a number, let's say that number has the digit D1, the digit D2, the digit 3T, and the digit D4. Now, if I say, tell me, can you create all the possible strings? This is like a sub question to this question. Can you create all the possible strings by swapping at most once, at most once, any two places at most one time, any 2 places in these digits, either let's say you pick up D1, swap it with D4, you pick up D2, swap it with D4, you pick up D1, swap it with D2, and so on. All the different possible combinations of strings that you would want to create in this particular I should say logic. If I tell you that this is what you want to do, then what will you actually answer? First of all, what is going to be your answer to say what are the total possible strings that could have been created with this? The answer is obvious. If let's say every digit is unique, then what am I trying to do? I'm just trying to pick up 2 places out of the total 4 places. In this case, let's say there are 4 digits. So out of the total 4 places, I'm trying to pick up 2 places and I'm trying to swap them to create a new combination. So can I say 4C2, or basically 4C2 is technically 6. The total amount of possible strings, if let's say I do want to swap, so the condition is I am swapping, if for a 4 lengthed digit or 4 lengthed number, in digits order can be 4C2, that's 6. And then one case is if you never swap, then plus 1. So this becomes 7. So the possible strings you can create for a 4-digit length string, all the different possible combinations you can create is maximum 7. And ideally, what we are looking for, did we not just discuss that the maximum number of digits your number individually can have is 7. So if I'm talking about 7, what is the worst case? 7C2, that is basically 7 into 3, right? That is 21 plus you do 1. What does this become? This becomes 22. So the possible combinations or strings you can create, or possible new numbers you can generate by swapping this, doing this one thing of swapping at most once, that means either you don't swap or you actually swap, but only one time, is maximum in this order. It's basically maximum 22. So what does this tell me? What does this intuition hit me? This intuition hits me is I can maybe run a brute force solution. How? You know that you're trying to pair up 2 numbers. So in a general, like a very beginner approach of pairing up 2 numbers is running 2 for loops. So I'll be like, I'll run one for loop. That's from I0. I is less than n, I plus plus. And then inside this, I can run another for loop. That's of the j pointer. That's I plus 1. J is less than again n and j plus plus. Now these 2 for loops, what are they helping me do? They're helping me go to each individual pairing of I and j. Correct? Now, when I'm standing at each pairing of I and j, what is left for me to do? All that is left for me to do is, if I have nums of I, I somehow want to make sure that this nums of I gets checked with all the possible combinations of nums of j, as in whatever are the possible strings, sorry, not strings, like I am saying strings many times, because what I'm trying to do is I'm trying to create individually string only, and then I'm trying to check. Why string? Because to handle this 0 case order extra which we just discussed, right? But we'll come to the code part and understand that part. But let's just say for this case, all the possible different swappings you did on nums of j and then the possible different numbers you created, I want to check that does nums of I pop anytime in this possible creations of nums of j. If it pops anywhere in this, let's say this is going to be, let's say, an array or something like that, or let's say maybe I can even keep some other data structure. We'll come to the code part and we'll look into that. But let's say this is like, just for simplicity purpose, this is like an array of all the possibilities of nums of j, right? All the possibilities or possible nums of j. Now, all the different swaps and possibles of nums of j, when it gives me a new array, then in that array I want to check whether nums of I occurs or not. If it occurs anywhere, if any one place nums of I comes, then will I say that yes, this current swapping that could have resulted for nums of j actually matched with nums of I? And if it matched with nums of I, can I say voila, I have received a case where I can say nums of I, and that swapped case of nums of j, whatever that came, I don't want to go into that part. Like, I don't need to check which was the what swapping happened to create the nums of j. Some swapping happened, some new nums of j came into picture from that swapping. Either one time it swapped or it did not swap at all, I don't care, but it still gave me nums of I back, which meant nums of I now and this new swapped number became almost same pair. So I can say, if that happens, can I increment my answer by 1? Yes, I can increment. So this is like a if condition. I can increment my answer by 1. And this is the general outlook of how I would try to create my logic. Now, if I look in the like, this is a very simulated brute solution at a very straightforward manner. The question to myself is, if I actually implement this and I utilize my time and energy to code this up, will this work? And this is the main question that happens with beginners. Let's say we want to write a problem and we never think of the brute solution once, you will never be able to optimize. So the doubt is currently, I have written a brute solution. That's very important for me to start off with something, some idea, some intuition. The next question would be, does this work? If it doesn't, then maybe I'll optimize. But if it works, why not code it up? So let's ask, this runs in O of n order. Yes. And this runs in O of n order. Any problem? No problem. So currently I have already occupied like an n square complexity. Now, if I look further, I need to generate this array, right? I need to generate this array. So for that generation, I'll call some helper function. So let's quickly discuss or get an idea of that helper function, right? If you want to get the possible different combinations of this nums of j, you can again in that helper function call something like this. You can be like, all right, I have an helper function. All right, I pass this nums of j, and then I can create 2 for loops inside this itself, right? Like, let me not call this nums of j. You can call this simply as some nums. So you want to calculate or pitch out all the possible combinations of this nums, or not rather nums rather. You can even say this as simple number, right? So how do you do that? Very ideal solution would be, you want a set, all right? But you don't want to have a high time complexity due to a set or some data structure which is keeping uniques. So I want a set or a map, but I don't want that extra time complexity to maintain that set or map. So I can go for an unordered set structure. So I can be like, I have an unordered set. Why an unordered set? Like, why I'm talking about unique? Because I know if a unique case is there, then I won't have that extra burden of those repeated possible combinations, right? So if I maintain that in a set, I know it's unique for me. Moreover, if I don't use a structure that gives me all the unique combinations, then there can be some repeated combination, and some repeated combination might get counted twice or more than once, basically, right? So I don't want that. That's why I want a set or a map. But if I don't want to keep that order, like I don't want to change the complexity or go in a higher complexity, I know I can maintain an unordered version of that. It is going to give me a constant time complexity while insertion and deletion or whatever you want. In this case, we are simply inserting. So yeah, that being the main case. So I have an unordered set. This is going to be of the string type, right? Why string type? Because I'm maintaining strings, right? And I'll maybe call this as possible strings. All right, so possible strings. And then what would be the ideal case? Ideal case would be I am able to double loop between all the possible places of digits I can swap in this nums number. And when I swap those two places, I will insert that new configuration of num inside this unordered set, or the unordered set in the string format. So this is basically going to be a string. And this is going to be the helper general outlook. Like I'm not going to very detail. We'll discuss more in the code part, but a general outlook of this helper function. Now this for loop is obviously going to have a maximum running capacity till the number of digits, right? If in this case, we discuss the maximum digits you can have is 7. So this runs in maximum 7 order. This runs in maximum 7 order. And then the insertion is constant. So this almost runs in like a 7 into 7. That's 49, or you can say 50 order. So again, very, very small. This is also like a 50 order. And then now we just discussed, if I want to iterate on this possible array, so to find this possible array, you took like a 50 order. So let's say you took a 50 order, and then you iterate on this possible array, the maximum capacity this possible, not array I can say. Now I'll have a set in this case, right? As we discussed now that we are trying to create a set. Now this set has a maximum size, we just discussed, like a 25 order. So not very big again. So to create that set, this helper function took like a 50 order, and then when you iterate in the set, it's like a 22 order. So overall I know that this check that's going is going something like n into it's like a 50 order maximum case, like a 50 order. So roughly, can you say if n and n is both, n is 100 rather, so can I say this is like 100 square into like a 50 order? So can you say this is approximately like a 10 power 5 order? Yes, it's approximately a 10 power 5 order. And will a 10 power 5 order work? Definitely works. So that is the whole idea, right? This is a simulative problem because the brute solution works. And that's the idea behind Leetcode. If we look at the first two problems, most of the times for the beginners, we only have to simulate the whole thing and it's going to work. All right, so let us look into the code part and try to understand how would we go about this approach, right? Just how I explained, right? So I'll go ahead with the extraction of the size of the nums. Then what I'm doing is I'm first finding the maximum number in the array, right? Why am I doing this? Because I know then that will help me fetch the highest limit on the digits I have, right? I get the maximum number. I simply say auto it in nums, mx becomes max of it comma mx, and then my digits stores conversion of toString of mx dot size. This gives me the highest limit on the digits that I can have in the particular array. All the highest number equivalent giving me the highest value of the digit length that can be there on the number of array, right? Number inside the array. So now once I have these digits, how will I utilize this? Next time I'm going to create a vector of string called array, right? I'm no longer going to work on this nums because this is of integer type. I want to work on strings, right? Remember, why do I want to work on strings? Because it's going to help me factor that extra space. Let's say I have this number 3. So I just explained. The number 3 currently looks like this, but technically in string format, this is something like this, like 0003. Right? So how about you work on this as a string now, rather 0003, and do the swaps wherever you want with using this helper function. That's why this possible strings I was using this word over here and not rather a single term 3. That's the whole idea. So I can say, all right, create a vector of string named array, and then go to every number inside this nums, push back inside this array the make digit function called with this number it and this maximum limit digits. Now what is this make digit function? Let's see. This make digit function is a very simple function. It takes the number, takes the digits, converts that number to string, and then whatever has the leftover space, if possible, in the leftmost side. How can I check that? If the current size is less than digits, that's the total limit. I know I want to insert some more zeros in the left part and concat that with num string. So if let's say I had 3 only, it will convert to 0003. If let's say 00003, if let's say I wanted 5 digits, right? So that's the whole idea. Simple enough. It runs maybe in a constant time complexity. I mean, you can have some time complexity for this part to concat and everything, but since we are maximum running in like 7 digits, I know it's not going to have a very big deal. It's still going to work, right? So Keeping that aside, I get like a constant time complexity, almost a constant time complexity, to push back inside this by making that in a digit format. Then I have the answer, starts with 0, simple 2 for looping of the pairing of I and j, 0 to n, then I plus 1 to n, I and j both declared. First, find the unordered set of string of possible strings by calling a make swap function, right? Make swap function looks very simple, the helper function we were talking about. How does that work? First, create an unordered set of possible strings, pass that num and digits from here. First, insert it directly in this set. That would mean I have never swapped, because I know at most once swapping is done. That means I either swap or I don't. So for never swapping, I insert it as it is. And if I want to swap, run these 2 for loops, 0 to digits, that's the highest limit I can go. And I plus 1 to digits, that's the next 2 for looping I can do. If both the characters are not equal, swap it, insert that, and then swap it again. Why swap it again? Because I want to reverse the effects I created from line number 18. Yes, because I want the original string to get back in its place. I don't want to maintain that swapping. Next time I have another swapping pair, I swap it again. For that, I want to retain the originality. So I'll swap it back again after swapping it once. And then I have come out and I return this possible strings. And then in this possible strings, I run a for loop, check whether any string s is equal to array of I or not. If it is, increment my answer, I am good to go, and this is the whole idea behind the problem. Alright, now what about the time complexity? I have some time complexity from here, I think like a constant time complexity, don't worry about that. Maybe you can call this time complexity as like a 6-7 time complexity. So what is going to happen if you look over here from here? You have the n order time complexity that runs in nums over here, so this is n. Then if you, let's say, just for considerable purpose, call this like a time complexity of concatenation, that's like a 6 order. So you get like a n into 6 order, but general case you can take it as n only because that's constant. So over here in n order, you create the new array. Then you have n into this 50. So this is like n into 50. Plus there is something more. This is like a 20. This is like a 20. You can say 20. Into, this is again for this checking, if s equal to array of I, there would be like a manual checking to each and every character. So you can say this is like a 6 or a 7 order checking more. But then again, this order checking, like if you consider this, you don't consider this inner term, like I am not taking a very broader picture, like I over here also just took a approximation like a 50 order, but like in a broader picture you can say this is in approximately going to still remain in like a 10 or maybe like a 100 order, you can say, like maximum. I don't think it's going to go in a 100 order basically, but even if let's say I take this in a 100 order, what's the worst case? This goes in like a 10 per 6 order, right? And in a 10 per 6 order, definitely this goes in a 10 per 6 order. So even in that case, I know the time complexity right now runs in 10 per 6, and 10 per 6 is also going to work. Yes, it's still going to work. It's still within my boundaries. It might work in a very minute way, might not be on the very borderline of the time complexity on which we could have failed on a TLE, but still definitely works, because ideal way, if you just calculate this, we are not crossing that boundary. We are still within the limit, right? And I can prove that simply by running this. If let's say I run this time complexity, this approximation of time complexity with the solution now, we'll see we get an accepted solution over here. Alright, yes, we get an accepted solution. So the whole idea is the brute manner. If you are able to understand that, yeah, I was able to create a brute force solution, then I will be good to go. I know I will not have to consider any other sort of a solution. And this is all about problem 2 of Leetcode. Up till problem 2, we just saw if you understand basic simulation and basic time complexity calculations, you can easily solve any problem that you want. Alright, so problem number 3, final array state after k multiplication operations 2. So this is like the second part to the first problem that we saw, right, problem 1. And the only difference in this problem is k is very large. Alright, so when we saw the first problem, we saw that k was very small, right, k was only in 10 order. When k was very small, we could have manually done a brute solution and simulated the whole process. This is the same question. It's still saying you need to perform k operations, but now k is very large. Look at k. K is in 10 power 9 order. And then again, nums of length is also very large. It's not again in 100 order. It's 10 power 4 order. Which means technically now I don't have the capability to simulate the process. I need to find some more optimized solution of the first part. So when I looked at the problem, my question to the question I asked myself was, how do I optimize this? Or better, what is a pattern that I might see while I want to optimize this? What do you mean by pattern? So it came to me that obviously, let's look at it like this. Let's say you have 5 numbers in the array. A1, A2, A3, A4, A5. And then what are you trying to do? Eventually at the very end, you're trying to achieve a final state where you have multiplied A1 with, let's say this multiplier is called m to the power of x1. Then this number looks something like this, A2 into m to the power of, let's say, x2, so on, so on. You can say this is A3 into m to the power of x5, where m is the multiplier we are talking about. And then this x1, x2, x3, so on. If you sum that up till x5, this is equal to k. This is what you're trying to do. To utilize the k operations, you're somehow distributing those k operations into like 5 places where you are saying, okay, m that multiplier m should go and multiply itself with that number, and then multiply it again, to some x1 times at this position, some x2 times at this position, some x3 times over here, so on, so on, till some x5 times over here. So that net multiplication times you did, all this operation you did, sums up to be k. This is the logic, right? This is what you're trying to simulate. Now, I ask myself is, at the very end, because now k is very large, I cannot manually simulate this. If somehow I'm able to come up to the conclusion that what is x1, what is x2, if somebody tells me, okay, x1 is 3, then will I try to manually simulate this? Can I not simply say I'll go to A1 and I'll say multiply m power 3 to this? Then if, let's say, somebody told me that this x2 was, let's say, 5, then I'll go to A2 and multiply m power 5 to it. If, let's say, somebody told me that x5 was, let's say, 7, then I'll go to A3 and multiply m power 7. So if somehow I'm able to calculate how much do I need to multiply m to every number, then I will be good to go. That would definitely much more optimize my solution, right? I will not have to simulate this thing. So this is the first place where my mind was working. Now the problem is I was not able to figure out any way of how do I come up with this exact x1, x2, x3 value. So what I said was, let's sit back, let's drop some test cases and see what can I observe. So what I've done over here is, I'll show you a simple code piece, and then for that code piece, I'll show you the output I've noted. What I did was simple. I created the size of the array, stored it. So, and then I created a vector of pair of int comma int of array. Now, what does this store? The first value stores the value, and the second value over here stores how many times multiplier has been multiplied. This is what I store. So I'll push back initially it comma 0 as a pair, as in it is the number, in nums it comma 0 as a pair in this array. That would signify that right now this number is it that at that location, and it has been multiplied with this multiplied 0 number of times. And then I simulate the process, same simulation from question number 1. I copy pasted this, simulated the same process. I said first find the minimum, then the index of that minimum, and then multiply that with the multiplier and increment the second by 1. And then what I did was I simply printed it.seconds out of this array. Now, what did it help me do? It helped me observe a very, very crucial thing, right? Let's look over here. I have actually jotted down the results. What I did was, for the first test case, that was 2, 1, 3, 5, 6, right? I varied my k from 0 to 20. And then I printed this array. So what it gave me was very, very interesting. So over here, you can even cross verify. If let's say over here k was 5, then the answer finally looked like 8, 4, 6, 5, 6. What did that mean? If you compare the first number, that's 8. The number 8 has been modified from 2. So if you see how much multiplier has been multiplied to this number 2 to get 8, you will say 2. It has been multiplied 2 times. 2 into 2 power 2 is basically 8. So if you look over here, for k equals to 5, the first value is 2. For k equals to 5, the first value is 2, which signifies that if k was 5, then I would have multiplied the first position by m 2 times. Similarly, I would have multiplied the second position by m 2 times, the third position by m only 1 time, the fourth position by m 0 times, and the fifth position by m 0 times. So this is for k equals to 5. I did this for all possible k's. I ran this logic. I inputted the test case and I ran this logic, and I said I'm going to do this for all possible cases to a certain limit so that maybe I can get a pattern. And I did find a pattern, and that pattern helped me get to a very crucial observation. So first I observed was, when you were at k equals to 0, nothing was multiplied, good to go. Then when k was 1, first you multiplied the second number by m. Then you multiplied this number. Then you multiplied the second position, so it incremented by 1. Then this over here, this position, then the fourth position, then again I think the third position, and then the fifth position. And this is where we stopped. After this, a very crucial observation. After this, if I look, what I observed was, if you now, the total size of the array was actually 5, right? The total size of the array was 5. So let's try to look up 5 pairs. All right. So what I'll do is, I think I should rub this from here so that it is much clearer in picture. 3, 3, 2, 1, 1. All right. So I'll note it down over here. For k equals to 10, you had 3, 3, 2, 1, 1. So what I did was, I paired up 5 total positions. So let's pair up these 5 positions, that is n equals to 5, and then these 5 positions. Observe one important thing. In this 5 positions, can you see that now, till k equals to 10, you multiplied m to individually each indice these many number of times. Now when you jump from k equals to 10 to 11, you multiplied the second value, then like the second value is multiplied by m, then you multiplied the fourth value, right? Then you multiplied, what we can say, the third value. Then you multiplied the last value. We can see this, and even better, like from jumping from 9, you multiplied the first value, right? Like this 2 became 3 when k was 10. So total of 5 pairs observed like this. First value multiplied, second value multiplied, fourth value, third value, fifth value. The order is not important, but observe this very carefully. Now if you observe the next set of numbers, see this again. First value multiplied, second value was multiplied by m, fourth value was multiplied by m, third value was multiplied by m, and then the fifth value was again multiplied by m. So can I say that after each and every 5 iterations, a cycle was repeating? A very, very important term. A cycle was repeating. Yes, it was. If you go even farther than this, you will very clearly observe this cycle. So what was happening is, since n was 5 over here, after a certain limit, 5 limited blocks was repeating in a cycle of saying that individually each number one time was getting multiplied with m. So over here, first number got multiplied, then second, then fourth, then third and fifth, and then again repetition. First, second, fourth, third, fifth. Again repetition. First, second, fourth, third, fifth, and so on, so on, so on, so on. So what does this tell me? This tells me that there is a pattern, there is a cycle. So now again, k is extending to 10 power 9. If k is extended to 10 power 9, can I simulate this? No, not at all. But now if I tell you that in this k equals to 10 power 9, there was a large chunk of portion which was actually a pattern of, let's say, 5, then will you not reduce your complexity by a very large margin? If I'm able to calculate how many chunks of these blocks were coming in this particular position, then can I simply say all I need to do, like if this is chunk number 1, if this is block or chunk number 2, similarly there is block number 3, block number 4, 5, 6 possible. If let's say there are f blocks possible, then what is the final case? The final case is you need to multiply f number of times m to this first position, m to the second position, m to the third position, fourth position and fifth position. That is the f blocks. And this is the whole idea. This is where my whole idea started to build. So my whole idea, like now I asked myself, why is this cycle repeating? What is happening over here is, what is happening so that this block is getting created? And the answer was pretty obvious. You can see that before 9, there was no pattern. Can I see any pattern? Like over here, the second element, then first element, then second element again, then third element. Then this was like first element again, then like second element, then like fourth element, then like third element, and then like fifth element. There is no pattern over here. Very haphazard manner. Why was there no pattern is, cleanly observe, one thing is very common. When you were still having 0 anywhere in this 5-sized array, which told you that some number has still not achieved a multiplication of m, until then your cycle was not at all visible. Once you reached a state where every number has been multiplied at least once by m, is after which you started receiving a pattern of 5 blocks. In this case, n blocks basically, but n is 5, so I'm taking 5 blocks. And then if you look over here, if let's say, assume that k was given 22 in the question, then what would you have done? You would have said, I would have brutally first achieved this state of, let's say, like approximately like 9 iterations. Good to go. 9 is very small. I can do 9. Yes, I can definitely do 9. So I'll do approximately 9 iterations. I won't hamper my test cases a lot. After this, I will quickly jump on blocks. quickly jump on blocks because I know I have some blocks left. And then let's say there is something that's left at the very end. In this case, you can see like I would have jumped 10 to 14 block, then 15 to 19 block. And then when I would have taken a mod with the leftover, some part would have still been left. Like some chunk would have still been left. Let's say over here, you can see one chunk is still left. So what you can do is simply iterate again in this leftover iteration like you did over here. So the whole idea was I was able to figure out a pattern. The pattern was very important. The pattern was telling me that till you were not, first of all, achieving every number to be multiplied by m at least once, there was direct brute force method. After which we observed that there were nn blocks getting repeated of multiplication, which could have been tackled by simply saying if f are the number of blocks, I will just multiply m power f to every number. And then there was some leftover part at the very end which could come by taking mod. I can just simulate it again. Alright, so this is the whole idea behind the problem. Now to implement this, there's going to be like a good chunk of code. So this, I should not say this is a very beginner friendly problem, right? We will use priority queue to actually implement this. Maybe you can find up a better implementation, but during contest, what I was able to understand is this solution seems the best to go ahead with. And to take into consideration this part of m power f. Now remember, this f blocks can be very small, right? Or can be very large. If let's say f is something like, let's say, maybe like, let's say, like since k is 10 power 9, right? K is 10 power 9. So let's say this f is 10 power 7. Will you go on to multiply m 10 power 7 times? No, you cannot. You cannot run a loop of 10 power 7 times to multiply m. So there is one more concept that comes into picture over here that actually makes this question not at all a beginner-friendly question, that is modulo exponentiation. Why? There is one thing known as binary exponentiation, but why I'm saying modulo? Because it was also given that you need to apply modulo every time of 10 power 9 plus 7, which is a prime. So there is a concept known as modulo exponentiation, which helps us, I'll write this down actually, modulo exponentiation, which helps us to calculate. What does it help us to calculate? Let's say I give you x, y and p. So it helps you calculate x power y whole modulo p. This is what it helps you calculate in a log y order, log of y order. Y means the power which you want to exponentiate x with. In that order, it tries to give you this output. And this is like a standard piece of code you can pick up from any template and anything you want. I also picked up back it from a template. And using this modulo explanation, now my question becomes very simple. Because this simulation is not going to run very largely. Why is it not going to run very largely? Also an important question. Imagine that this simulation, when does that simulation stop? This simulation stop till every number has received at least one multiplication. When will that happen? Let's assume you had a very, very small number and then you had a very large number. So you know that in this case, if let's say the multiplier is, let's say the multiplier is 1. Then if the multiplier is 1, then the answer itself is the nums array. But if multiplier is 2 or more than 2, then even if it's 2, it's like the multiplier m is 2, then this small number is going to reach towards this large number and get multiplied so on in a log base 2 order. Right? And the highest difference you have right now in nums of I is like 1 and 10 power 9. So maybe I can say this small number is 1, this large number is 10 power 9. If 1 has to travel to 10 power 9 and cover this middle range by getting multiplied with m, you will maximum have log power 2 of 10 power 9 order. So which is approximately like, I think like, it's like I think 45 iterations. I don't exactly remember, but very, very low iterations. So this inner state achievement is not going to run in more than like 100 iterations, like approximation. That's a very standard approximation. Again, this was like a hit and trial method to run the code, figure out some mathematics and do, but this doesn't look very, very long. Right, this initial state, if I call this IS, initial state, the achievement of this initial state in a brute manner, just like how we did in the first question, is not going to take a lot of complexity. And then you are simply jumping over the blocks, because if you now know n and you know k, you can simply calculate k by n, and that is the number of blocks you will receive. K by n is going to be the value of f, that's the number of blocks. So you can then simply multiply every number with m power f by binary exponentiation. That's again in log terms, so good to go. And then the last simulation will also be very small. Why? Because you would have done, last simulation would be k mod n. So k mod n would have told you how much chunk is still left. Now remember, if you do k mod n, K is like, if you do K more n, K is basically 10 power 9. And then this nums is 10 power 4. You have already extracted a large chunk of portion. So this chunk of portion is also not going to be a very high limit. Like maximum it will go in 10 power 4 or 10 power 5 order only, which tells you that yes, this solution does make sense. I can still run this and it's going to work. All right, exactly. I think the better approximation would be in 10 power 4 order only, because that is the total size of this nums array, right? This nums array. So when you exhaust the chunks fully, you know that you will not be left with a lot of margin at the very end. So you can say still a good to go order, and I'm still going to run in a decent complexity. All right. So this is the whole idea behind the problem. Now this is a very not at all a beginner friendly problem. So I still repeat, you can look at the code, try to pause the video, understand the code on your own, make up some test cases, and it's going to make sense to you. All right. So that's the whole idea. So what we'll do is we'll look at the code part. I'll remove this now, since this was like the example code I was using to tell you all the observations I did, and this is the main logic. All right. So let me just uncomment it. Now I have a multiplier. I'll say if multiplier is 1, then I know I'll return nums as it is. I don't need to go anything beyond. Good to go. Now I'll create n, that's the num size. First I find the maximum element. Simply by running a maximum element function, dereference it, I get the max value. Then I create a priority queue. Priority queue is going to be the pair of int, int type. Why do I need a priority queue? Because first of all, I want to prioritize on the min heap by taking the first value to be the value that has still not been multiplied with them. Because remember, the operation is saying you find the minimum value, and then that minimum value is going to help you. The operation should be multiplied on that minimum value. So to achieve that, maintain a priority queue. So the first value becomes that value. And then the second is that index. Why do I need an index again? Because I know I'm not changing the orders otherwise. I want to return the final state of the array. So I need to keep that order. So inside the for loop, I will first push nums of I, I. This creates a priority queue with me, and now in the priority queue I have maintained on the first order of pair, that's the value. Whichever is the smaller value gets sorted first, and then if some values are same, first index, whatever is the leftmost index, gets sorted first. So you write nums of I, and this gets you the correct ordering of minimized thing at the front of the priority queue. Now once you have this logic, now you can apply a while loop. In this while loop, you can say two things. First of all, K should be there. Like if I know I want to find the initial state, this ith state I'm trying to achieve, but to receive this initial state, up till here, K should also be available. So till K is there, and. How do I check this logic that I have every number has still been multiplied by the case? That can be very simply said by simply saying, if the mx is given to me, how am I trying to get this logic? I'll multiply the top first element, like top element, that's the pq.top, of that first, that's the value, with this multiplier. When I multiply it, if it's still less than equal to mx, that means there is still some margin to receive the initial state. If there is still some margin to receive an initial state, I'll say decrement k, first extract the value, that's the multiplier into pq.top first, the index, that's pq.top second, and then push back again this val and index in this particular priority queue and pop back whatever is the leftover part. And this is what gives me, I think I misplaced this and I should have kept it over here. Yeah. So pop back that out and then push back the new value, that's the value into index. And this is going to get again inserted in the priority queue, and then the priority queue again, since it's a priority queue, it maintains the order. It's going to min heap it out, and it's going to heapify the whole thing, and it's going to maintain the order for me, where the first value is the minimum. The first pair's first value is the minimum, and then order has been done. And I keep on doing this, either these two conditions false. Either I exhaust K, that's one thing. If I exhaust K, that means I never have to go in this blocked way of getting the logic. Maybe somewhere only here I stop. Let's say K was 5. If K was 5, then you will stop only here only. Like if K was 5, you stop here only. You never go in this block logic. That's also one case. Other cases, if you don't exhaust K, other case would be, in that case, this initial state would achieve if everything has been multiplied at least once. If everything has been multiplied at least once, that means the number will no longer be equal to the maximum. It would go above maximum, because maximum was declared by you or kept by you once you were starting off with the initial array. But now the array is continuously changing. Now elements are continuously changing. So if it goes above max, if the least element in the array has gone above max, that means every element has been modified in such a manner that there is at least one multiplier getting multiplied to every number and an initial state has been achieved. And then you can stop. Once you have stopped, now comes the main logic. How do I calculate this block part? Block part is simply k by n. So I pass k by n in the mod power function. That's the binary exponentiation. I don't want to explain binary exponentiation. This is like a standard logic. You simply pass the base and the exponentiation and you calculate the mod value and you print the result. So what I'll do is I'll pass the multiplier. That's m power f. F is k by n. So I pass k by n inside this and this gives me the power, the value that I want to multiply. And then again in the priority queue I'll go. I'll see till how much I can pop till it's empty. That would simply, like the current size of the priority queue anyways would be n only, in n order only. So I'll simply extract the value, the index, and I'll pop it. And then I'll ask myself, one thing can be like you popped it. So when you will go on popping it, you will go to the first element, then the second element, then the so on. So whichever is the smallest element currently, that requires the next iteration. So you can say that is k mod n greater than 0? Like this can be written as greater than 0. If k mod n is greater than 0, that would means I will multiply it with m power f, that's obvious, but there would be some chunk still left. If some chunk is still left, that means I need to multiply it with pow, that's obvious, but I also need to multiply it with one more multiplier, right? One more m, because that one more m is going to be that chunk part, like it's k equals to 20. One more time you have to multiply this first number, right? You can see this 4 to 5 change. That means you multiply the first element with the value m again. So there's one extra m that's getting multiplied is coming from the fact that is still some k left. And that can be checked by simply saying is k mod n still greater than 0? If it is, that means there is some chunk left. So decrease k and multiplier and power both in this nums of index. And once you do this, store that in nums of index. Else if k mod n has turned to be equal to 0, that means now you you made k minus so on and it went to 0. That means it did not go to 0. K mod n went to 0. That means now you don't have any chunk left. So the rest over elements only need an m power f multiplication. That means simply multiplied it with power value. That's this value we calculated. This is like m power f we were talking about, right? So this is the whole idea cumulated into a small code. Again, this can be detailed out maybe in a much larger way. Maybe that makes sense. But over here, just for contest purpose, this is what made sense to me. So I just dropped it down. All right. So this is the whole idea. Now, once I say that, I have finally popped out each and every element. Once now I return nums will have the accurate final state. And this is going to give me the right solution. All right. So what is the time complexity now? I have a priority queue over here, that's n log n order, right? Why n? N is the loop, and then why log n? Log n because to insert in the priority queue, you require a log n time complexity. So this is n log n to maintain every pushing number inside the power. Now this while loop is going to break either one thing. If k is very small, then it breaks, or this happens. And this thing is going to happen as we explained. It's like maximum small number to large number approximation would be like 40 to 50 order. So you can say that this condition is going to return, it's going to become false in like a 50 to 60 iterations max, or like maybe even up around 100 iterations. That's all. So you can say that this while loop runs in an approximation. Again, I'm taking approximation, like in a 100 order. And then this pushing back is also like log n factor. So you can take maybe this log n factor again inside this, which is still very easy enough to go, not at all a very high time complexity. Now this m to power f calculation is in log y. Right, log y, where y is the power. Y means k by n. So this is like k by n. Now k is basically 10 power 9. And if let's say n is very small, if let's say n is 1, then this would be log 10 power 9. 10 power 9. And log 10 power 9 again would be like let me just check. If log base 2 10 power 9, 10 power 9. How much is it? I think, okay, we can actually input this out quickly and we'll get this. 1, 2, 3, 4, 5, 6, 7, 8, 9. Alright, so I'll calculate this out. We'll have a better approximation. So this is very small. This is like 30 iterations only. So I think then that means we can write this over here. Not even like 100, I can keep this something like even maybe lesser iteration, like even 50 iterations, and that's going to work, right? Very, very small, right? And then this exponentiation is also like a 50 order. Like I'm taking again very higher upper bound, right? And then this while loop, this is going to run in like n order because you are running this
popping out every number, and the maximum numbers you have are basically n order only, right? So you're popping and pushing and popping every time. So in the priority queue, you have maximum n numbers getting maintained at a time. So you, in this case, since you are only popping out, you pop it out and then you get the correct thing and you never push back anything. So no extra time complexity for that part. All right. So overall, I can say like a better time complexity solution would be to simply say this is like n log n factor, right? You don't need to go into the very depth of if is this 50 or 40 or 30 or 60 and so on. Not very intricate maths is required. A general idea by looking at the solution looks like n log n order, right? Which definitely works because n log n means 10 power 4 into 10 power 4 base log n. That would be like 20 iterations max. So you can say n log n is a good time complexity, definitely works. And what about space? Since I'm using this priority queue, and it's storing at max this n elements, you can say. So I can say priority queue is giving me an n order extra added to maintain these n elements in the priority queue. All right. So this is the whole idea behind the problem. This is the whole observation behind the problem. So it's kind of like a ad hoc problem, definitely not beginner friendly since it involved by modulo exponentiation. So if you don't know this concept, you will not be able to solve that chunky, that block chunk issue of multiplying m power f. And then again, that being said, this brings us to the end of our problem 3. I hope you liked it. Let's move on to the 4th problem. All right. All right. So last problem, problem number 4. Count almost equal pairs 2. Now this is the same problem as the problem 1, right? Same problem as we discussed of problem 1, and even the solution is almost the same. The only difference is that in this version, the number of operations that can be performed has been increased to twice. All right. That means you cannot swap at most once. You can swap at most twice. All right. Now the problem with this is, if let's say I copy paste the same solution from 1, will it work? Obviously no. Why? Because right now we have a solution that looks something like this, like a n into n, that's like only coming from this I and j outer for looping. All right. And then this helper function is running by you saying that I'm swapping one time in like a total of digits order, like a digits order. This is like a d into d again, right? This is the approximation that was happening inside this function only. We can just revise this again. Yeah. If you look over here, this was like a 7 into 7. That was the maximum case that we were talking about, right? So this was like a 50 order, or in better, you can simply say digits, right? It depending on the digits, whatever is the maximum digits I pass inside this. So digits into digits order. Now, if you have, let's say, digits that have been, first of all, look over here. You have nums that has been increased to 5000. So now n into n is basically 5000. This is 5000 square. And then you have 2 swaps. So if you want 2 swaps in a brute manner, I can write 4 for loops. Inside this for loop, inside this for loop, inside this again one more for loop, inside this one more for loop. So I will have 4 for loops. Will run in d into d into d into d. This is going to be the order. So if this is the case, this is like d4. And what is the maximum digits am I talking about? Now the maximum digits I'm talking about is basically like it's less than 10 power 7. So you can say I have like 7 to 8 digits again, right? So this is like a 7 square or something, you can say, sorry, 7 power 4 or something. So now the problem is 7 power 4 is not very big. It's not very big. It's like 7 power 4 is 20, this is like 49 into, that would give you like 49 to 49. So this is like a 49 to 49 square, which is like approximately 50 square, which is like 2500, like approximation 2500. That's the value. But this 5000 square is very big, right? This 5000 square is very big. I know that it's giving me a very high time complexity right now. So I need some optimization rather in my problem. If I'm able to optimize my code number 1, then maybe I can just copy paste that same code and maybe my code number 2 will run with some approximations. All right. So what is the optimization we can do? So very, very common approximation that was very clearly visible when I read this problem was this part. Remember, we are trying to pair up I and j. But what is the final outcome of this? The final outcome of this is, once you find all the possible combinations of saying that this is like the possible combinations of nums of j, you try to compare it with nums of I, and you're trying to do it every time. Can I make this logic go in one for loop? That's the whole idea. One for loop. Can I do that? The answer is yes. How do I do that? What can I do? I can maintain an unordered map. All right, an unordered map. And that unordered map can go on storing nums of I continuously once I end one iteration, or sorry, not one iteration, once I end one array of I can create this unordered map, since it will have a constant time complexity, and add that, like increment the frequency of array of I inside this unordered map. Now, how is it going to help me? It's going to help me because if you look at it like this, like let's say you had an example, you had let's say something like this, you had like 30, then you had like something like 21, then you had something like 12, and then you had something like 03. All right. So now once you have this case, what are you ideally wishing? You're ideally wishing that, let's say, or even better, like let's say this was also 12. This is going to be much better. Now let's say this was 12. You know that this 12 is going to get paired with this 21, and this 12 is also going to get paired with this 12 over here. So if I want to calculate this, then how do I do this? You go to 12, you say, all right, you up till 12 nothing came, so let me add this 12 to a map, and now I have 12 inside a map. Now next time when I'm at 21, I also say that, yeah, this 21 currently, I'm going to make this 21 go inside my map again. So inside the map, I have 12 again, and I have 21 again. But when I go to this 12 again, this 12 should have gotten paired with this 21, and this 12 also should have gotten paired with this 21. So how about if I only incremented the frequency of 12 and I paired this with this 21, can I directly get the answer? This is like a very crucial and very standard concept which we use when we want to convert this I, j pairing and the counting to see that if I am talking about I, j pairing, why not save that in a map, and then I know all I need to match is the number of frequencies that match with my current condition. So my current condition is some nums of j matches with some nums of I. That's my current condition. So if I'm able to save the frequency continuously, or in this case, I don't want nums on nums. If I modify that would have become array, right? I just modified this in array right over here. So just like naming convention, if some nums of j matches with some nums of I, and I go on saving their frequency in an ordered map, I will not hamper my time complexity into an n square, but rather I can do this in order of n only. How? Let's look into this. All right. So I'll show you the code part for the fourth problem, and it's going to be very simple now. No explanation needed otherwise. What we'll do is same thing. You have the same function. Let's make digit function, same thing. You call the same size, calculate the maximum number, calculate the digits, and then in an array, push back the digits in the string format. But now, rather than running two for loops, so look at what I've done. I create an unordered map, MP. First, I'll increment the first frequency, that's array of zeros frequency by 1, because that is the one frequency that has already come. Int answer is 0. Now look, I start off my loop with not 0, but rather 1. I equals to 1, that's the first index. Go on. Calculate the possible strings from the make swap functions, right? I'll discuss the make swap again because I know I have also one more change to do. I know I'm doing at most twice. So I'll look into that, how am I doing that. But just assume it's going to give me all the correct possible strings, just as for assumption. Let's see it assume that it does. So when it gives me all the possible strings, what will happen is I'll run a for loop inside this possible strings, and I'll see, is any occurrence of this S present in the map? If it is, then I know that all such occurrences is going to get utilized by pairing that with that current array of I. Because up till here, if it is already present, then that means those all together frequencies can be kept as a pair with current array of I. So rather than doing another for loop, I did another for loop of j. I have quickly computed how many previously stored strings in this map were getting utilized to form a pair with array of I. And I simply add all those frequencies to my answer whenever I find it. So if I find it, map of MP of S added, good to go. And then I will simply end this for loop once I've exhausted all the S strings. Now, once I've exhausted all these S strings in the possible string format, I'm going to increment array of I by 1 again, so that the next string is added by 1 frequency, and the next string, and the next string, and the next string, and it helps me maintain that net strings every time I have in this map. So next time I'd never have to run one more for loop to create this extra n square bracket. And now if I look in this time complexity order, this is n order, inside this, I don't have any n order extra, right? So let's go back to this make swap functions. Now in this make swap changes function, remember you are doing this at most twice logic. So how do I do that? One loop for this digits, so it runs in like a 7 order. Then one more loop for this digits. So this is like swap number 1. If nums of I is not equal to nums of j, you swap it. So this is first swap. First swap you did. Now first swap is done. Because you have the power to do one more swap, what you can do is you first insert this, insert with one swap only. In the case that insert with one swap, that means if let's say you only require to do one swap, that's one possible combination. Swap it up and insert it. And then do this for looping again. So again runs in 7 order, again runs in 7 order, same thing, just over here. I 0 2 digits, I plus 1 2 digits, this is I1 to 0 2 digits, J1 from, this can be called as 0 to less than digits. And then again run this thing. If you see that you have already done the swapping before, continue. And if you have not done the swapping, same logic again. Check whether it is equal to not, and then swap it up. Swap. So this is like swap for second time, right? Insert with 2 swaps, and then this is the reverse swap for the originality, or coming back, or reversing the effect, reversing the effect of second swap. And then when I come out of this loop, I again swap, because this way is the reversing the effect of first swap. And then when I finally end this for loop, like 4 times for loop, very brute solution, you can say, very in a simple case, you come off with a possible strings over here unordered set, and you can simply return it. So as we discussed, it has like an approximate, like I'm taking a very high upper bound, like a 2500 solution, because this is like a 7 power 4. You can actually calculate 7 power 4. I don't exactly remember, like 7 power 4 can be like, yeah, 2400. So like a general approximation, 2500 I just took. And then you are running this for loop in 2500 order. So this is 2500 order. And then you are running this iteration, simply finding and then adding. And because this is an unordered map, you are having constant time complexity for everything. This find also runs in constant, this add also runs in constant, this insertion also runs in constant. So overall, in a rough manner, I'm not saying very approximated, but in a rough manner, the time complexity now is n into 2500. Now, if you take n to be 5000, this is like 5000 into 2500, which can be written as like 125, and then you have 1 2 3 1 2, which is basically like approximately like in say 10 power 7 order, right? That's a good approximation, right? Which is on the borderline. Again, it's not very fast, but it's on the borderline of 10 power 8. So it's going to work. All right. And what about the space? Again, space is dependent on the size of this unordered map. Now, previously in the problem we saw, we were forming approximately like NC2 or digit C2 solutions, right? Over here, since you are swapping twice, NC2 or digit C2 into digit C2. That's going to be the case. So you can say this is going to be approximately like 21 into 21, or in a very rough order, you can say this like as that's if like 21 square is approximately, I think 441. All right. So I can say maybe like a maximum order of 500, right? I like a very upper bound. I'm taking a very upper bound again. I'm not taking exact approximation. A very upper bound. I know that space is also decent enough. I won't have a lot of possible strings are going to get stored in this unordered set. So in a approximated manner, the time complexity and space are fitted. They are fit in the boundary. They're just on the borderline, but they're still within my boundary. And if I run this, I think I'll get an accepted solution. Might be a bit slow as compared to the other users, but again, that's all we're looking for to get an AC. And yes, definitely beats, and we have an accepted solution over here. All right, so again, the whole idea behind the problem over here, I tried to create the solution in such manner was, how do I optimize the first solution in a beginner, that's the beginner's code, into a advanced code? That was all my case. Now, I know this problem can be solved maybe with some other logic where you don't go with such overhead of a solution of 10 power 7, maybe something even less than this. But 10 power 7 is still on the borderline, still works. And the idea of this conversion from I, j pairing to unordered map is very, very important for everyone to understand. So I hope this is a learning point for you. And this brute solution again inside this is very simple to understand. 2 for loops inside 2 for loops. So that's anyways decent enough to go. And that is going to help us solve the full and final fourth problem. Alright, so thank you everyone for watching. I hope you like the PCD.